Like Newton, there was another famous scientist, an astronomer named Johann Kepler, who also had three laws. His three laws were the laws of planetary motion. They were actually related to Newton's laws. And we're going to look at these three laws here with this diagram that we have here. The first law of Kepler was that it was called the law of ellipses. The law of ellipses. Kepler decided that orbits of like planets, like the planets around the sun, are not actually circular. They're fairly circular, but they are actually ellipses. The paths of the planets about the sun are elliptical in shape, and with this sun being at one focus, and as the planet goes around in this orbit around the ellipse, and so there's at points your planet comes closer to the sun, like right here, and sometimes it's a little bit out farther away from the sun. The closest approach that a planet gets to the sun is called the perihelion. The perihelion. Helion refers to the sun, and para is the closest that it gets to it. The furthest away, at this point right here, is called the aphelion, or the aphelion. Sometimes I think people say the aphelion. This is just if you're going around the sun. So like if we're talking about a satellite that's actually going around the Earth, so like we have the Earth here and some satellite going around it in some kind of an elliptical shape, the closest it ever gets to it, this isn't very good, the closest it gets to it is called the perigee. G refers to the Earth. Perigee, and the apogee is the farthest away that a satellite will get from the Earth. But law one, Kepler's first law, is that the planets actually trace out an ellipse with the sun being at the focus. The second law is called the law of equal areas. The law of equal areas. And this law says that if you have like an imaginary line drawn from the center of the sun to the center of the planet, that line will sweep out equal areas in equal intervals of time. So I could go like 6 months and this planet would get from here to here, and I could measure the area of this little triangle here, and that area would always be the same. So for any 6 months of time, it would sweep out equal area. So if I had 6 months from here to here, then that area right there would be equal to this area right here. And of course, if you're going to have the law of equal areas, then that means that the further away the planet is, the slower it's going. And so as it comes in close towards its perihelion, it actually is going to speed up and kind of slingshot around, because it's going to speed up because it's closer to the sun, and there's more gravity pulling it. So as it comes around here, it's going to go at its fastest rate through here, so that the area of this triangle could be equal to the area of this triangle here. And the third law, which is the most important and really the mathematical one where we can determine things, is called the Law of Harmonies. Scientists, astronomers always were looking for harmonies of the planets. They called them the you might have heard this in some religious songs, the musical spheres. They have harmonies of the planets, how they were all dancing in kind of unison with each other. And the law of harmonies is basically just a ratio. And it says that if you measure the period of a planet, so the period is how much time it takes to go around one orbit. The period of the planet, up here it says P, but usually we use the capital. We use a capital T, just like the pendulum equation, a capital T for period. How long it takes to get around, that is related of course, to like in this ellipse, you have halfway across this A is called the semi-major axis. But basically, that distance would be the average distance from the sun to the planet. So sometimes we're closer, sometimes we're further away. And if you averaged how far we are from here to here and here to here, you would get about halfway across this ellipse. So the ratio is, if I take the period of any planet, so I take the period of a certain planet, planet 1, we'll say, and I square it, and then I divide it by the period of some other planet. Maybe this planet's further out, and I square that period. Then it's related to the cubes of their semi-major axis, or basically the radius of their orbit. So the radius, the distance from the sun to the planet, planet 1 cubed over the distance to the planet 2 cubed. So the law of harmonies basically states that the ratio of the squares of the periods of any two planets is equal to the ratio of the cubes of their average distances from the sun. So the ratio of the squares of the periods of two planets is going to be equal to the ratio of the cubes of those two planets. So we can kind of set up I guess a little problem here. Let's say we have we'll have the sun here shining, and we're going to have Earth, we'll say, is out here, and it's orbiting the sun. This should be elliptical, but I just didn't draw it very good, I guess. And then we have, we'll say we have Jupiter, clear out here. It's a big planet, and it's orbiting the sun also, something like this. And let's say that the distance from the sun to the Earth, I'll try to do this in the right color. Distance to the sun to the Earth is about 93 million miles. So I'm going to put 93. I'm just going to put 93 and hope, well, I'm going to put 93 million. 93 million miles from the sun to the Earth. And for Jupiter, it's about 483 million miles. It's a long ways away. Okay, I want to know how many days, we'll say, how many days, Earth days, would it take for Jupiter to go all the way around one time? So what is the period of Jupiter is what we're really asking there in days. Okay, so what we're going to do is we're just going to use the law of harmonies, because the square of the period should equal the cube of the distances away from the sun. So if I want to find, I'll have this T1 be the period of Jupiter. So I'm going to have the period of Jupiter squared over the period of Earth squared. Well, how many days does it take the Earth to go around one time? See, that we actually know that. That's 365.25, we'll just leave that part off, squared days. And then we're going to look at our cubed ratios of their distances away. So on the top, we had the period of Jupiter squared. We're going to have the distance out to Jupiter cubed, and that was 483 million miles. But since they're both millions, we'll just leave that part off, and we'll just do cubed. And then the distance out to Earth cubed is 93 cubed. So we take 365 squared times 483 cubed and divide that by 93 cubed. And then we're going to take that answer and we're going to take the square root of it so that we can get the period of Jupiter. And if you put that in your calculator real quick, and you'll be able to validate this answer is correct. It'd be 4,323 Earth days it takes for Jupiter to get all the way around. So when the Earth goes around in 365 days, the Jupiter, it's going to take 4,323 days. Well, if it takes the Earth, 1 year to get around, how many Earth years is it going to take for? So if the Earth goes around the sun in one time, in 1 year, how long? Well, let's do it this way. If Jupiter goes all the way around, like a Jupiter a year, how many Earth years is a Jupiter a year? So when this Jupiter gets all the way around here, how many times will Earth have gone around the sun? So we can take this days right here and we can divide it by 365. And you'll see that it's going to take about 11.8, well, about 12 years, about 12 Earth years for Jupiter to go from here all the way around back to the same spot. So the Earth is going to go around the sun about 12 times. It's going to take 12 years before Jupiter makes it all the way around one time. And we can use that with Kepler's third law, very important law right there, is the Law of Harmonies. The square of the periods is equal to the cubes of the distances to those planets. Now we're going to, in one of the next videos, hopefully simplify that a little bit. We use certain measurements to make that a little bit easier. So you'll have to tune in again for that video.